Hello, everybody, and welcome back to another lecture in Geography 341, Weather and Society. I'm Dr. Zach Hilgendorf, and in this lecture, we're going to be talking about ocean circulation and currents. And you might be wondering why we're talking about ocean circulation and currents in a weather class. Well, if we think of the broad distribution of thermal energy across our planet, one of the ways that that thermal energy is mobilized is through differences in pressure and through differences in temperature. So if we look at how our ocean currents circulate across our world, it's driven by something we call thermo-haline circulation, which is thermo, temperature, haline, salt. And we'll talk about what that is a little bit later, but this big, massive circulation of ocean currents across our world drives weather patterns across our world as well. We'll talk about that in this video and the next one, focusing on things like El Nino or ENSO events. But stay tuned and let's get rolling. So first off, big thank you to my PhD advisor, colleague now, Dr. Ian Walker, for supplying me with the slides for this one. This is from a course he was teaching at University of California, Santa Barbara. He was kind enough to share them with me. I have modified them a little bit, but primarily his construct. So thanks, Ian. I appreciate it. So let's start by looking at Earth as a giant conveyor belt. And we've talked about this a little bit before. We talked about this in the pressure. We talked about this looking at heat distribution. We talked about this considering winds. All these different aspects that drive change and movement of energy across our world are also happening in the oceans. We look at this as the ocean conveyor belt, right? This massive system of oceanic circulation that moves nutrients and energy across our world. And we can see in that picture on the right, just above my head there, just one of the many maps you can see showing local ocean currents. Here we're looking primarily at the jet, or the Gulf Stream current, which is kind of running from the Gulf of Mexico under the panhandle of Florida, north along the east coast and off into the North Atlantic. So in this video, we're going to talk about what are ocean currents, what causes them, how do surface winds create ocean currents, what's a geostrophic gyre, and how do we relate them to ocean or atmospheric circulation, how do gyres influence local climates or regional currents, and then what is ocean upwelling and downwelling. So first off, let's start with the easy one. What are ocean currents? These are continuous, predictable, directional movements of water within the ocean. Think of it like wind, right? The jet stream, for example. We have a good idea of where the jet stream is going to be. It can meander, it can move, but it's more or less predictable and continuous. It can move both horizontally across the surface and vertically up and down within the water column. Horizontal expressions are surface currents and deep ocean currents. Vertical expressions are through upwelling and downwelling. And these are driven by gravity, wind shear, and water density, so temperature and salinity, that thermo-haline aspect that I mentioned previously. So if we look at wind-driven currents, we might recall from our video on winds across the surface, when wind blows, it exerts a shearing force on the surface. It also happens on the ocean surface. Remember that boundary layer that we talked about before. What this produces is wind-driven surface currents. So current energy or speed is roughly about 3% of the wind speed. If we look at this picture that my face is currently over, we see a bunch of different colors. Those are expressions of velocity in ocean currents in centimeters per second, not meters per second, centimeters per second. So the fastest, we look at that Gulf Stream, may be moving upwards of a meter a second. It varies significantly from place to place. The fastest ocean currents are somewhere around the nature of 2 to 3 meters per second or 6 to 10 kilometers per hour. We see that, for example, the Gulf Stream on the east coast of the United States. Kind of drifts off into the North Atlantic. We see that going towards kind of Greenland and Iceland area. So how do wind currents develop? Well, wind is blowing over the ocean surface. That surface shear force causes surface waters to move with the wind. There's a frictional drag that causes deeper layers to be dragged along as well. The influence of wind shear and strength of currents decreases with depth, and that's really important. Because if we look here, that energy is transmitted downward by what we call turbulent motion. Turbulent motion just means that there's a mixing that's going on within the fluid. It basically acts like gears that drag the water along. So if we look at the top here, these are much larger than these ones and these ones. And you can imagine smaller ones down here until that energy is dissipated for the most part. Stronger and longer winds exert more energy on the surface, which leads to greater turbulence and faster and deeper currents, surface currents at least. Consider wind blowing to the north in the northern hemisphere. Surface layers of water start to move northward with that wind. At the surface, frictional forces oppose some of that motion, causing turbulent energy exchanges into the deeper layers. Beneath the surface, the Coriolis force, which we've talked about before, acts to deflect motion towards the right, similar to wind flow in the atmosphere that we talked about a couple of weeks ago. And then surface currents are moving 45 degrees to the right of wind stresses in the northern hemisphere, or 45 degrees to the left in the southern hemisphere. So we can see here you've got wind acting in this vector, friction acting in this vector, the Coriolis force acting in this vector, and the surface current moving this way here. We saw this before, right? This is our direction of rotation of the world going this way. It varies from roughly 1,600 kilometers per hour near the equator to 0 kilometers per hour near the poles. And we have this mixing. We see here this turbulence, this grand circulation within our atmosphere driven by things like the Coriolis effect. So one of the really important concepts then to recall or to consider is what we call the Ekman spiral. This equation at least was solved by a gentleman named Walfrid Ekman for wind-generated surface currents. His name was he lived from 1874 to 1954. He's Swedish. He's a Swedish scientist, and he theorized this first in 1902. So basically what happens is when surface water molecules move by the force of the wind, they in turn drag deeper layers of water molecules below them. We kind of just talked about this, right? You have these turbulent exchanges between layers along with Coriolis deflection in the upper ocean. And that basically causes the entire column to be set in motion. So each layer is moved by friction from the shallower layer, and each deeper layer moves more slowly than that layer above it. We see that here, right? Until around a depth of about 100 meters or so, that movement ceases. So like the surface water, however, the deeper water is deflected by the Coriolis force. Again, in the northern hemisphere to the right and the southern hemisphere to the left. As a result, each successively deeper layer moves more slowly to the right or left, creating a spiraling effect, an Ekman spiral. Because the deeper layers of water move more slowly than the shallower layers, they tend to twist around and flow opposite to the surface currents. You can kind of see that here. You've got these vectors going this way. By the time you're down at depth, they're going this way. Mean flow is here, and our wind stresses are at that angle there. So Ekman transport is an important mixing and energy exchange process in the surface ocean. This is really important to think about because it's one, transferring energy deeper into the water column or dissipating energy deeper into the water column. And it's also moving material that's in that spiral up and down with the column as well. From Ekman transport to global circulation, we can see Ekman transport is dominant in this direction and this direction based off of our trade winds, which we see here, our northeast trade winds and our westerlies. Here we see kind of this surplus water accumulation here within the center of our oceans. So water accumulates in between wind circulation up to 2 meters high with very small slope from that high to low elevation. We can kind of see it here. We've got this lens, if you will, of accumulated surface water, almost bulging off the surface there. This creates a pressure gradient, or from one, gravity, F sub g, that moves water away from the center. The Coriolis force is pushing in towards the center, opposite to that pressure gradient. And then if the two forces are equal and opposite, we have geostrophic balance. We talked about geostrophic winds and geostrophic balance before. So flow around the center of that water accumulation lens leads to the generation of a geostrophic gyre, which we can see here. So we have this rotational flow of surface waters that are linked to atmospheric circulation. These winds, these trade winds are directly related based off of the trade winds and Ekman transport to these big ocean gyres. And ocean gyres essentially are these systems that move in this big circular motion. We see them, we can kind of see here. This big circular motion. Now, that is really important, again, for mixing of materials and energy across our oceans. We have these large gyres at about 20 to 30 degrees north or south latitude associated with these big, typical subtropical high anticyclones. We talked about those in our atmospheric section and atmospheric pressure system not too long ago. The smaller gyres in the North Atlantic and North Pacific near 50 degrees north that rotate with the polar low pressure cyclones. There are other small gyres as well. We can look at those here. We can see a number of different gyres. We've got the Pacific ones, the Atlantic current maybe a little bit, this here, we see this big gyre, the North Equatorial current to the Kuroshio current. This is a big Pacific gyre. We see a couple others kind of down here. Have this big rotation here. Off in the Atlantic, the South Atlantic as well. These gyres are kind of everywhere. See our North Pacific, our South Pacific, and our North Atlantic. Delete my rambling sketches here. The South Atlantic, and the Indian Ocean. So these four dominant gyres can do some pretty interesting things. Not sure if we've ever heard of the Great Pacific Garbage Patch before, but it's basically plastic that's been dumped into the oceans that will follow ocean currents, eventually ending up along another coast or accumulating in the open ocean. The Great Pacific Garbage Patch is a result of this big gyre that sets up in the Pacific. So there are a few different versions of it. We got our Western Garbage Patch over here, got some more over here, and then we have our Eastern Garbage Patch. So the Eastern one, this whole thing is kind of associated with these different atmospheric systems. The Eastern Garbage Patch is kind of associated with that North Pacific subtropical high that we see here. We can see in the figure below the NOAA one there, that is the modeled mass concentration in kilograms per kilometer squared. Now, it doesn't just look like a big pile of trash. There's a bunch of stuff in it. There's kelp and plankton and algae and fish, other creatures living in this garbage patch, but it is a massive garbage patch. 46% of that total mass is made up of discarded fishing gear, which is pretty disheartening to think about. 8% microplastics, 13% mesoplastics, 26% macroplastics, and 53% megaplastics. 1.8 trillion pieces of plastic on estimate. 80,000 tons of garbage. 99% of everything in that is plastic. And we can see it here kind of drifting off the coast of Hawaii. This kind of ellipsoidal pattern here. Now, how do gyres influence regional climates? Well, warmer eastern shores like southeast of the United States are there because of warmer currents like the Gulf Stream. Cooler western shores like northwest Africa, for example, are colder because of the Canary currents, these cold water currents with descending cooler water from the northern portions of the oceans, where here we've got this equatorial water being dragged up, or here this water being dragged up as well. It can also promote upwelling of cold waters from the deep ocean. And we'll get to upwelling here in just a second, but based off of where this water is coming from, it can actually drive temperatures to be different, or weather patterns to be different than they typically would at just their latitude alone, because we are dealing with an exchange of energy from either higher energy to lower energy, higher pressure to lower pressure, hotter to colder. If you look at the Gulf Stream, for example, we see the western boundary current, the west side of the gyre. It's one of the fastest in the world, over 2 to 3 meters per second. It's basically, think of it, you can see it. Oh, I'm going to need a different color here. You can see it here. I'm highlighting it with my cursor. Here as well. Eddies here and kind of continues off. So like a river, basically like a different density style river, we've got this warm water moving through our oceans, basically pulling this water up. Where's my, oh, I've lost my, there it is. Pulling this water up from these equatorial regions northward along the east coast of the United States, moderating that temperature and warming that temperature. Basically, you're left with these eddies of warm or colder conditions that we can see here off the coast. Draw it up here. Off the coast a little bit, but towards the coast, in this region over here, we can see that these warm temperatures are leading to warmer conditions right along the continental shelf on the Atlantic side. We look at energy or heat transfers in the oceans and atmosphere. Look at the percent of heat energy transported poleward by oceans and by atmosphere. At greater than 60 degrees latitude, it's only about 9.2% is transferred poleward by the oceans, whereas 90.8% is transferred poleward by our atmosphere. But if you get down to the lower latitudes in the equatorial regions, if you're below 10 degrees north or south latitude, 59% of that energy is being exchanged by the oceans, whereas only 41% is being exchanged and moved poleward by the atmosphere. So you can see it drops off pretty substantially. We go from, if we were to look at a basic graph here, 10, 20, 30, 40, 50, 60, and this is percent for our oceans. Tough to do this with a mouse. There we go. Anywho. And here we go from 10, 20, 30, 40, 50, 60, 70, 80, 90, more or less. We go from roughly 60 immediately down to roughly 15. Kind of bounce up a little bit and then flatten back out until we get to roughly 60 and we start to drop off again. It's a lot that's driven by the oceans near the equator and transferred poleward. Get rid of that here. So when you really look at it, the atmosphere and oceans are coupled systems. The oceans store heat, the atmosphere moves heat. And we know that. We've talked about that before. So ocean circulation strongly depends on the atmosphere. And what we'll get to next, density differences, temperature and salinity gradients within the ocean and within the water column. So we look at convection and heat flux in the oceans. The atmosphere is heated from below by heat flux from the warming land or the ocean surfaces. Warm air rises, it's less dense. Cold air sinks, it's more dense. This is what we call convection. Now, in contrast to that, our oceans are heated from above by solar radiation at the ocean's surface. Warm water does not sink. Cold water does not rise. We have a stability condition. There's no convection occurring here. So what you end up with is temperature in the ocean decreases with depth. We call this a thermocline. So here we've got a mixed layer near the surface. If we look at our figure on the side here, that very quickly drops off and kind of flattens out with depth again. So you go from roughly 23 degrees Celsius, just below the surface, to an average of less than 4 degrees Celsius as you get towards that, kilometer and a half into the water column. There are latitudinal variations with that, obviously, as there is with everything. We looked at temperature, latitudinal temperature gradients, but the same happens in the ocean. So there are seasonal thermoclines in the mid-latitudes, so 45s, 30s, 45s, 60s, right around there. And you can see kind of how that is expressed here. Kind of a more gradual, more rapid drop off as you go down in the column versus more gradual drop off. In the low latitudes, it's pretty permanent as you go down from, this is 500 here. Same thing, I'll sketch that out. We got 500 here. So as you go down right around that 5 to 600 level, you drop off pretty rapidly. In the high latitudes, 70, 80, 90 degrees latitude, you're pretty consistent. There's actually an inversion here. So we drop off at the surface, but then because of that exchange in deep water ocean currents, we're actually warming up a little bit to a little bit above freezing as you go further down in depth. Now, recall, changes in temperature, salinity, and pressure or depth control the density of seawater. We mentioned that briefly at the onset of the video here. Density increases as temperature decreases, it increases as salinity increases, and it increases as pressure increases. All result in an increase in mass within a volume of water. Generally speaking, temperature and salinity are the most important controls on density. This results in what we call thermo-haline stratification, these density layers within the water column. Now we look at the Atlantic north to south thermo-haline circulation. We are looking at this big, broad distribution of salinity and temperature that cycles through the area here. So we can look here. This is the distribution of temperature within ocean waters. So notice that we've got some areas that are quite warm. Primarily, it is quite cold. Now, these differences lead to circulations within the ocean currents, these gyres that we were talking about in a lot of ways. That look something like this. So differences in that temperature salinity are causing our water to cycle. Let's see it here. Sometimes it moves into these shallower areas. moves up, moves into the Gulf Stream area, the Atlantic, inverts, flips back down, becomes, you can see what's going on here. We have this shallow current, warm and less salty, and deep currents, which is much colder and much saltier. It can take hundreds to thousands of years for a single molecule of water to complete this cycle. Now, what's important to note, and we can see here just kind of our dominant currents across. We've got our California current, the Humboldt-Peru current, our Gulf Stream, the North Atlantic Drift, the Canary, Brazil, Benguela, Aguilas, the West Australia, East Australia current, and the Kuroshio current. These all have different impacts. Now you can see if you look back a couple slides, you'll see where we have these warm ocean currents along this way here, and we've got this kind of muddled mess up here, and then generally speaking we've got these colder currents here. A lot of this is driven by this thermo-haline circulation. Now if we look at density and seawater density here, we can see a pretty broad change. So as we go deeper and deeper and deeper, our water is getting colder and it's getting denser. You can see that here. And then look down here, the Antarctic bottom. This is the coldest and densest seawater that we have. It's kind of descending off of the shelf of Antarctica and dropping down to the bottom of the ocean. So convection or vertical exchange between surface and deep ocean waters will only happen when surface water density is greater than or equal to deeper waters. So something interesting happens here. Once we get to a certain point, our waters will sink. How can surface waters increase in density? There are really three primary ways. We can either cool it, make it saltier, or a mix of both. Now, there are only a couple different regions where we have these basically sinking zones, these deep water formation zones. Basically, where this occurs, surface water is overturned and sinks. Somewhere else, deep ocean water must then return to the surface. Basically, if we think back to our law of conservation of mass, this is a major conveyor belt. Now, the two main places that this is happening are in the North Atlantic and the Southern Ocean near Antarctica. Because these locations fuel the ocean's global conveyor belts, they're important for Earth's climate. Look back at our thermo-haline circulation here. This area here is a deep water formation point, and this here is a deep water formation point. So that's where you've got this deeper water descending down back into the depths of the oceans rather than being a warmer ocean current on top. So if we look at the northern Atlantic thermo-haline circulation, we have our wind-driven surface currents to the Gulf Stream, which is rapidly bringing this warmer water northward. As it does so, as it brings this water north here, it starts to cool and evaporate and become saltier and colder and denser and sinks. Right? Much of that water returns southward in the gyre circulation, but some of it continues to the north. So a lot of that is just cycling around. But the water that doesn't kind of gets caught up into this thermo-haline circulation cell. It becomes so dense and sinks to the bottom, forming a very slow southward flowing bottom current. So here we can see what happens. So we've got our warm Gulf Stream waters coming here, evaporating, condensing, but salt is becoming denser, and it's flowing back to the south here. Now, recent evidence has suggested that the Gulf Stream circulation system, or what we call the North Atlantic Meridional Overturning Circulation, or AMOC, is starting to slow down. That's concerning. So if we look at changes in sea surface temperature, most of them are getting warmer. But here it's not. In this area here, it's kind of tough to see, but try to sketch out as best I can here. We're seeing a plume of colder anomalous temperatures. So ocean temperatures in the North Atlantic are cooling down, contrary to what's happening in the rest of the world's oceans. Warming, why is that? Well, a few different reasons. One, you've got the Greenland ice sheet that is rapidly melting with current changes in Earth's atmosphere and temperature distribution. And this is really concerning because the exchange of warm and cold water in the AMOC region feeds these global circulation patterns, these deep ocean currents. And if it stops, we don't really know what's going to happen. The repercussions are kind of unfathomable by us today. So that continual formation of deep waters in the North Atlantic pulls warm surface water northward and vastly influences Earth's climate. Like I said, these regions of deep water formation in the North Atlantic are right next to a giant ice sheet, the Greenland ice sheet. And as that ice is melting, we've got this influx of fresh, cold water. And what it's doing is it's starting to throw off the AMOC, this Atlantic Meridional Ocean Current. We can ask ourselves, what'll happen to the density of surface water and the formation rates of deep water if that ice sheet melts? Well, to our best understanding, density will decrease due to increased freshwater inputs, making it less dense, making it harder to form that deep water. We think it might be slowing down because of this effect, and the region is now heavily instrumented with sensors to track the strength of surface and deep ocean currents, because if this shuts down, we're losing a big exchange of energy across our world. And again, we don't know what the repercussions of that will be. So moving into the last couple slides here, coastal upwelling. So we talked about Ekman transport before. This basically refers to the upward movement of cold, nutrient-rich water along the coast. It's caused by alongshore currents and offshore Ekman transport. And we see that here and here. This results in biologically productive waters because it's moving nutrients around. Downwelling can also occur where Ekman transport is oriented towards the shore, northbound or on a west coast, for example. So instead of upwelling here, we're downwelling here because that Ekman flow is being deflected this way. We're getting a general movement down. It's common on western coasts of some continents. We see it here in the United States, along the coast of California, along a couple places along the west coast of Africa, and then along the coast of kind of Peru, Chile area. Now, surface wind rotation around subtropical high pressure systems kind of drives this, along with boundary currents from offshore-oriented Ekman transport. Now, the effect of this is a moderate either cooling and or drying of local climates. There are some pretty big deserts associated along these regions. Now, if we were to look at a little bit closer to home, or the closest place where this is occurring, for example, California, that upwelling along the central coast brings cold, nutrient-rich waters in phytoplankton with high concentrations of chlorophyll, making these biologically important processes. And it also leads to something called the marine layer. So cold water from upwelling currents promotes the formation of a marine layer. And we talked about this in the diabatic processes of the fog generation lecture a good little while back, where you basically have the formation of what we call a marine layer, this low-lying coastal fog or cloud cover region. It's basically caused by a temperature inversion in the air over the water. We've got basically a temperature difference, these two different air masses meeting, condensing, and leading to the generation of this near surface fog. the cold marine air below warm descending dry air from the mountains. So moisture condenses in the air into this cool marine layer, forming fog and low-lying clouds. So that's going to wrap it up for this video. In this video, we talked about wind-driven currents, gyres, thermo-haline circulation, and coastal upwelling. In the next one, we're going to talk briefly about things like El Nino Southern Oscillation, Pacific Decadal Oscillation, these different trends within ocean currents that drive temporary weather patterns across our world. So I hope you enjoyed the video, and we will see you in the next one. Thank you much. Bye.